Hey guys, welcome back. Well, I've been taking some time to learn a new programming language called Python. Many of you have heard of it and probably use it. This is my first foray into it. I've been using a scriptable language kind of similar to MATLAB called Scilab for work and for some of the astrophotography related coding that I've been doing. And I used to use C++ once upon a time and Fortran even longer back than that. But this Python I saw on a recent YouTube video on a channel that I subscribe to called Dr. Becky. She's an astrophysicist, and she did a video in which she summarized 5 ways she uses code as an astrophysicist. And funny thing is, when I look at that list of 5 things she puts out, all 5 of those things that she mentions are things that I do at work, and sometimes related to my astrophotography work. So I thought, well, what the heck, I'll take a look at Python and see what it's got, and in the meantime, program up some of the applications I've written for myself in Scilab. I'll program them up in Python and maybe make them available as standalone executables up on the Google Drive. I use the Python 3.9, the core language interpreter. PyCharm is kind of an integrated development environment where you write and run and debug your programs. NumPy is a numerical library with a lot of things that you'd need to do some of the numerical analysis. And Matplotlib is a plotting library that produces plots very similar in format, and command-wise is very similar to what is in MATLAB. So I have some familiarity with that. And PyInstaller is a program that allows you to convert a .py, the script language interpreted version of the program, into a .exe file that presumably others can run. We'll find out. I'll upload my version of the program up on the Google Drive and we'll find out if it works or not. It'll be a Windows program, so those of you with Macs or Linux may be out of the consideration here, but there may be some emulators that you can get to run it. I don't know. Once upon a time, about a year ago, I did a study as I was expanding my telescopes to include wider fields of view. I also wanted to get a better handle on what DSOs are up there that I can see from my backyard, and then sort through them for those particular DSOs that were suitable for imaging. And then I put that into another video, and it's in a PowerPoint file that I use with pictures and the days when those targets become optimally available for imaging, and you can go check out those videos if you haven't already seen them. But in this case, I thought this first program, which is written in Scilab, would be a good guinea pig to learn Python on, so that's what I did. I rewrote this program in Python and also took the step to eliminate the patched together DSO catalogs that I had put together when I ran my first analysis of this, and instead have the Python version of the program read the text version of the Stellarium DSO database, which you can download, and I'll show you the link for that a little bit later. But anyway, it provides a more consistent library, a larger library. It has over 94,000 entries in the DSO catalog for Stellarium. Now, not all of those are things you want to take a picture of necessarily, but there are 95,000 items. It is consistent in the sense that if a particular target is both a Messier object and an NGC object, you can prioritize which one you want to call it. And in my case, if it's a Messier object, then I give it the M designation. If it's an sharpless catalog item, then I give it the sharpless number, and then if it's not one of those, I give it the NGC, and if it's not an NGC, I give it the IC number, and then that's where I stop. I don't do PGC or UGC, etc. So that's what I'm doing with this particular program. And while we're at it, why don't we go take a look at the Stellarium database, and I'll show you what it looks like. Now, the Stellarium database that you use within Stellarium is a binary version of this, and theoretically there is a process that you can use to take a text version of their catalog and turn it into a binary version. I have tried that. I have not gotten it to work, at least not on my version of Stellarium. Maybe it doesn't work. Maybe I just did it wrong. I don't know. But that's neither here nor there. Anyway, this is the Stellarium catalog. It has a number of, there's that long header here, header meaning there's no data. This number sign means it's a comment, but it tells you what every column in the database is. So there's the RA, the DEC, magnitude, there's the size of the object, and then there's various catalogs, and it'll give a catalog number. For example, if it's an NGC object, there'll be the corresponding NGC number in column 17. And if you scroll down, this is where the data begin. And so the first object, it's just given number 1 in the catalog. That'll become important a little bit later. But there's the RA, the deck. There's the type of the object. So what kind of a galaxy, what kind of a nebula. In this case, that seems to indicate that it's a star. The C plus N is a star cluster plus nebulosity, H2 region, dark nebula, open cluster, galaxy, etc. So I don't pull out open clusters and I don't pull out stars. And some of the other items I don't tend to pull out, but galaxies and nebula I do pull out in this program. And then you see it's just a ton of numbers separated by tabs, and that goes on all the way down to the catalog until you get to item number or catalog entry number 94,671. And in that case, it's an open cluster, and then you have some a summary of information here as comments. Anyway, this is the file that you will download or can download if you run this program. And this Python version of my program will read through this. The whole point for me in creating this program was to be able to put in my local horizons so that when I'm blocked to the south with my house here, I don't find DSOs that are only visible, that are theoretically visible but are hidden by the house. So I didn't want to include those in my study. Now, one of the things that I've found recently is that I've had to include the chimney here of the neighbor's house because I've had a number of objects cross the chimney and really screw up guiding. For example, the Trifid Nebula, the Gourd Nebula, the Sculptor Galaxy all pass right through this little window here, and then when they hit the chimney I lose guiding and the rest of the data for the night is screwed up if I don't do something about it. So knowing when and where I'm going to hit that chimney is a big factor in planning out the choreography of a night's imaging session if I'm looking at one of those targets that happens to flow between the edge of the house here and the chimney here. When you put together your version of your horizon, it's a format that is totally compatible with, and just like you would use if you have your horizon included in Stellarium or Cars2CL, it's just a text file with 2 columns of numbers, starting with the azimuth, 0 being north, 90 being east, 180 being south, and then continuing on around to north again at 360. So when you make your version of your horizon, make sure you start at 0, make sure you end at 360, make sure that the altitude angle in degrees is the same at 0 as it is at 360, and then based on whatever your horizon looks like, just fill in your numbers, as many as you like, as many as you need, and then my program will go in and interpolate in between these angles to find a corresponding altitude angle for a given azimuth that the individual target is at. But it's a very simple thing. Don't put any comments in this file. Just make it very simple. Make sure you hit return at the end of the line here so this is a completed line, and then everything will work out just fine. Now, let's show you how to run this little executable file. The astroplan.exe is the file you can download if you want to. The Stellarium catalog is the catalog of Stellarium objects we looked at, renamed to Stellarium_catalog.txt. And then the horizon file is a file name you create. Whatever file name you want to use is fine. You'll have an opportunity to enter it. In my case, it's called my_horizon. Now, after you run this the first time, it's going to store some of the input variables that you type in that if you run it a second time, you can just hit return and put in the default values. But the first time you run this .ini file won't be there. So I'm going to go ahead and delete that. And now let's go ahead and start this thing up. And the first thing it asks you is, what is your latitude? So I'm just going to make up some numbers that are close to where I am just to keep the entry level fairly quickly. So I'm going to say I'm at 30 degrees latitude, north latitude. I'm at minus 90-ish west longitude. And my local horizon file name is the one I just showed you, which is my_horizon.txt. There's 94,000 items in the table. I said you don't want a list of 94,000 results. So we need to cull these down a bit. There may be some targets that will poke up above the horizon, and you can legitimately see them, but you don't necessarily want to image them because they're not up for a long enough period of time to collect data on. Otherwise, it would take days and days and days and days to collect the data for a given for that given target. So one of the numbers I use to limit the number of targets that this thing finds is that I insist that the target be available for 4 hours of imaging within the constraints of the horizon as you define it in your file, and a minimum horizon that high horizon level or altitude level that I'll show you. But so if I put in 4 hours, I find that 3.7 hours is needed to get some of those targets I mentioned that go between the chimney. That chimney cuts out some of that time. So I put in 3.7. You could put in whatever you want. If you put in 6 hours, you're going to get a lot fewer targets. If you put in 1 hour, you're going to get a lot more targets. Enter the minimum peak altitude. This is, again, on the best day for this particular target, I insist that it must get up to a maximum altitude of 30 degrees. Now, obviously, it can be lower, and I don't tend to image too much below 30 degrees for many targets, but sometimes if it's on the southern horizon for me, then I'm stuck with what I have. If I want to take a picture of it, I've just got to cave in and image close to the horizon as needed. So I'm going to leave that at 30 degrees. Now, the minimum observation altitude is an altitude that's used, for example, as an override on your own horizon. You may be out in the middle of a prairie and your horizon is 0 all the way around. Your altitude restriction is 0. Well, this would restrict it to 15 in this case, in this default number, and that's what I tend to use. So you could, for example, I don't tend to do imaging below 20 degrees, so if I could say 20 degrees, which will insist that targets must get above 20 degrees before they will be considered visible. They must get higher than 30 degrees to be considered a useful target. Even though it's visible, a useful imaging target must get above 30 degrees, and it must stay above, in this case, 20 degrees or your local horizon, whichever controls, for a minimum of 3.7 hours. Otherwise, I don't consider it a target, or I don't want to waste time trying to collect data on it. Now, the minimum size of the DSO is important. If you have a long focal length scope, you can see and image quite effectively very small size targets. If you have a 80 millimeter refractor, for example, you may not want to put in a size of 4 because you're not going to want to take a picture of 4 arc-minute targets. You're going to want to take a picture of maybe at the lowest 20 arc-minute size targets. So for me, I have an SCT, and so I tend to use a 2.5 arc-minutes as the lower limit. Now, the lowest catalog number, this is how we restrict the amount of the range of that 94,000 element catalog if we want to. And I would recommend you do this when you first run the program, just to keep it from going crazy and spitting out 94,000 graphs. So the lowest catalog number is 1. That seems like a logical thing. The highest catalog number is 100. Let's go ahead and change that to 200. So it will go down and consider the first 200 entries and check each one of those for the visibility constraints that we have just defined. Now, when I hit return here, it's going to write this information out to a file, the .ini file, and it's going to start the analysis, going through and finding targets after a year-long simulation of the Earth going around the Sun and checking each of the 94, well, in this case, the first 200 targets. And you can see it's running pretty quickly. It found M45. It tells you a few additional information just to let you know it's working and cranking through stuff. So we've got an SH2 object, that's the Cave Nebula, and we have an NGC object, a 6979, which is a supernova remnant, it looks like. Actually, that's part of the Cygnus Loop, or the Eastern-Western Veil combo. And then we have NGC-24, a galaxy, and another active galaxy, AGX, and NGC-100 is also an active galaxy. So it's finding these fairly quickly. You can see we're up to number 182 now. We're only going up to 200 in this little reduced version of the file. And then at the end, it will summarize the number of galaxies found and the number of nebula found, and it produces a number of files. So now we started with just this series of files here. The first thing it does is prints out a version of the horizon that we've seen already. Then it prints out various files along here for each of the targets found, and we'll go into that, look at that in a minute. The second thing it does, it produces a catalog, which is the same format as the Stellarium catalog, but only has those objects that are visible from your situation. If, for example, you were able to convert this catalog into the binary form so that Stellarium could use it, then you wouldn't be confronted with all of the DSOs that are up there. You'd only see the DSOs that perhaps you want to take a picture of. So this could be a useful thing. I've never done this yet. Again, as I said, I've had trouble getting Stellarium to convert a text version of the catalog into a binary version, so this is on the wish list of things to figure out. And then there's a DSO list. I'm going to show you the full one. I won't show you that right now. And then there's a number of plots, and we'll go through what each one of these are. Now, the first thing, let's go through and look at when I ran the code the first time. Let me show you what this output looked like when I ran it for the full 95,000 items. And here is that CSV file. So if you double click it, it's going to load up in Microsoft Excel. And these are all the targets that you can see from your backyard. In this case, this is my backyard set of targets. There's only like over 1,000 of them, so there's some work to do to cull them down. But if I center them like this, these are all the numbers that were in the Stellarium catalog. Here's the name. You can see I've got M31. There's Andromeda Galaxy, the Cave Nebula, etc. Here. The RA, the deck. The type is either a 0 or a 1. If it's a 0, it's a nebula. If it's a 1, it's a galaxy. The size in arc minutes. The imaging score, which is a number between 0 and something close to 1, but over 1, probably less than 1.25. Basically, it's a combination of how high does the target get in the sky. So that angle, maximum altitude angle divided by 90 times the number of hours that target is visible based on your horizon divided by, I think, 10.5 or 10.25 hours. And so that product of those two numbers, both will be large when the target is flying right overhead and is up for a long time. So imaging scores around 1 are very good. There's a 1.03 right there. And this is the month and the day when that target will be most optimally available for imaging, meaning you can get the most imaging time on that target starting on that day. All right, so let's go by and look at the one of the plots that are produced for NGC 266 to see what its visibility history is throughout the year. And those are all stored in figures that are created by the program. Okay, so I've got all the plots. These are all the targets. Each one, IC302, for example, is a figure. I'm going to scroll down until we find NGC 266. I'm sorted by name here, so it should be in order. So there's NGC 266. Let's just pull that up. And as you can see, it's a plot, actually two plots. On the lower plot, what you're seeing is the number of hours NGC 266 is visible and on what day of the year it is visible. So for example, in January, it's coming down 6 hours available. And then by the middle of March, just after the middle of March, it disappears. So it's not visible for me anyway, for roughly a 2-month period until a little after the 1st of May, so around mid-May to a quarter into May. And then it starts to become available and visible for more and more hours until we get up to the optimum imaging time, which is defined here as a peak observing score of 1.05, which occurs here about a little into October, the first week of October. And so this is the time when you would want to start considering doing imaging if you want to minimize the amount of days that you've got to string together to observe this target. And so it's available for over 10 hours that particular night. So you could wrap this target up in one night, maybe 2 nights, if you had good weather and good cooperation from the moon, because after all, this target is going to be going from a minimum altitude of about a little over 20 degrees, for example, in here. Then it gets up to a maximum altitude of almost 90 degrees. So that's why it has such a high observation score, is because it's passing right overhead and it's up for a long period of time. Those two things kind of go together. But this is what every target that this program finds is going to produce a chart like this, so it kind of gives you an idea of when, for astrophotography planning, when to go out and put this target on the list. You don't want to try to decide you're going to image NGC 266 in February, as it is right now, because you only have it. It's only visible for 2 hours a night, for example. So you don't want to do that. You want to wait till it's optimally available, or near so that you can spend the least amount of time imaging and collecting images on that target, and then you move on to some other target. Now, this is one of the big picture plots that the program produces. It just basically summarizes for every galaxy, every nebula that it comes up with that you can see from your backyard, given your horizon restrictions, an RA versus DEC coordinates of those targets, and there's a very clear pattern that emerges here. Obviously, nebula lie in the plane of our galaxy, and because plane of the galaxy is tilted to relative to our equatorial plane, we see a sinusoidal character to the nebula, which obviously lie in our galactic plane. And because they are in our galactic plane, we can't see through those nebula, interstellar, intergalactic gas to see the galaxies beyond. So that's why we don't tend to see galaxies where there are nebula, and we don't tend to see nebula where there are galaxies, because the galaxies that we're looking at are above or below the galactic plane, because that they're not obscured by intergalactic dust. This is another big picture view. Again, in this case, it's plotted as a function of the day of the year, and we can again see galaxies and nebula divided. And we often speak of galaxy season. Well, that's the time of year when we are facing away from the center of the galaxy, and our nighttime is full of galaxies, as opposed to the nebula that are on the other side. When we swing around 6 months later, our nighttime side faces the plane of the galaxy, the center of the galaxy, our galaxy, and as a result we can see more nebula. And then we get into the span of time in between, where we get a smattering of galaxies and nebula. You can also see here the effect of the longer nights that we have in the January through March time frame, so we get much higher imaging scores because the targets are available for a longer period of time. And in the longer day period of our year, in the May through August time frame, imaging scores are depressed because there's not that many hours in the night. Newsflash, the best imaging time is when the nights are the longest. Some of you may have already figured that out by now. Now, this is kind of an interesting looking graph just because it's so geometrical, but it also says some fairly obvious things when you stop to think about it. First of all, we have the imaging score. So the best targets for imaging are these here, the ones that are toughest to image, meaning you're imaging down close to the horizon, you don't get that many hours per night, just more trouble to image targets with a low imaging score than it is to image targets with a high imaging score. One of the things that is striking about this plot is the triangular nature of it. There is the peak targets, the highest observing scores occur at a declination angle, or targets with a declination angle of 33 degrees. I live with a latitude of 33 degrees north, and if you draw a line from the center of the Earth out through my telescope pointing straight up, well, straight up is at 33 degrees. That line is at 33 degrees relative to the equatorial plane, and of course that's also the declination angle of targets. That's how we define declination of targets. Your highest imaging scores are going to be those with a declination equal to your latitude. If you have a latitude of minus 33 degrees, then this peak, this triangle, is going to move over to the left. Now, this edge over here, these are the targets that are really close to the horizon. And in theory, if I were to draw a line tangent to the Earth and perpendicular to this red line here coming down, that would be a declination angle of 33 degrees minus 90 degrees, which is about 57 degrees, which is where this is. So in theory, a target that has a declination coordinate of 53 degrees will just get to my southern horizon and then fall back down again. So it might just poke above the horizon for a second and then be gone. Well, clearly I can't take a picture of that. And also, I don't want to image down at 5 degrees, 10 degrees, 15 degrees. If I limit my imaging to 30 degrees, you've got to get a target in the southern viewable from the southern hemisphere has to get up to, for me, at least to a minimum of 30 degrees above the horizon. That's one of those parameters we typed in when we're running the program. Then, if I set that 30 degrees, that's what defines this outer limit, the outer extent of this triangular region. So these are all targets that, for somebody living at a minus 25 degree latitude in the southern hemisphere, these would be the targets that are going right overhead for you. For me, these are the targets that are very difficult to take a picture of because they're close to the horizon. They are only up for a few hours of imaging time per night on the best of nights. And so these are the challenging targets, but if it's an interesting target, then yeah, well, I kind of want to take a picture of it. So that's why I want to know about it, but I don't want to know about targets that I just have no intention. It's just not practical to take pictures of. Anyway, these are the kind of pictures that will come out of this, and it's important to remember your best imaging targets are going to be those targets that have a declination equal to your latitude. Another interesting plot is the imaging score, again, versus the size of the target. Now, it's a smattering of targets, but you can see right off the bat that most targets, most galaxies, are small. Okay, each one of these divisions is about 4 arc minutes. So within about 8 arc minutes, that cuts out most of the galaxies that we would be imaging. But this is where you need to consider your imaging setup. In my case, I've got 4 different telescopes. I've got one camera, the ASI 1600, and the pairing of the imaging sensor size together with the focal length of the telescope tell me what its range of the maximum size object can be to fit in that field of view. And of course, if you say, well, I don't want to take a picture of a target that has a that's less than 1/10 the size of my imaging sensor dimension, then maybe that provides a cutoff for specifying the minimum DSO size that you would consider when running this program. So for me, with my nominally 2,220 millimeter focal length SCT, I've decided to do a cutoff at 2.5 degrees, but I can see targets that are up to 25 arc minutes will fit in the field of view. So this covers most of the galaxy targets, as you might expect for a long focal length telescope like that. And then if you go down to my 100 millimeter ED102, it has a 700 millimeter focal length. And it's no point in wasting time taking pictures of tiny little galaxies, but I can start to get in some of these nebula targets here, and a pretty good range of those are seen here. And if I go to my William Optics 81, I'm surely moving out of nebula or out of galaxy world. There's a handful of galaxies here that might be worth taking a picture of. They'll be small in the field of view, but still maybe worth taking a picture of. But I'm getting a much broader range of nebula targets to take a picture of. And finally, my Red Cat 51 with its 250 millimeter focal length. I'm pretty much blocked out of most galaxies. There's certainly M31 is out here, and M33 is here, and then there's maybe a few that you might want to spend some time on. I'm sure one of these is M101, but there are some galaxies there that you might want to spend some time on with the Red Cat. But mostly the Red Cat is intended to capture large nebula targets, as shown here. But anyway, you might want to be careful and think about what your imaging system or systems are, so that when you define the minimum size of the DSOs that you're interested in, you can cut out a lot of these very small targets if, for example, you have an 81 millimeter refractor. Okay, so here are the steps to use Astroplan.exe. First of all, you can download Astroplan.exe from my Google Drive. In the video description, I give a link for that. Put that in a directory, and then download the Stellarium so-called Nebula database. It's an ASCII text format database called catalog.txt using this site here. There may be other locations for this as well, and there may be more current versions of this elsewhere. I don't know. Do a Google search and find your best one. Now, when you get that catalog.txt, go ahead and rename it to Stellarium_catalog.txt, because that's what it's called in the program, and put that in the same directory as the Astroplan.exe file that you download. Then, if you haven't already, create a local horizon file that reflects the azimuth altitude limitations based on where your telescope is located and the blockages that you have going around in a 360-degree circle. Execute Astroplan.exe just as I showed you, by double-clicking on the icon, and enter the information as I was showing you how to do. If your computer doesn't explode, well, have fun sorting through the 1,000 DSOs that you've never heard of, because that takes a good bit of time. Okay, guys, well, I guess that's about all I have for you today. Clear skies, and the next round of DSOs is on me. Talk to you later.